Hey everybody, welcome back to Future in Space. My name is Tony Darnell from deepastronomy.space, right there in the little lower third there. Welcome back to another, I'm glad we're doing these again. I'm so happy we're back doing these Hangouts. Today we're going to be talking about something that I know I'm really curious about, and I know you guys are too, about nuclear thermal propulsion. Now, this is one of these topics that seems to me like we should have solved this by now, right? I mean, we should have this already. And so, this technology that we're going to be discussing today is based on something that people have been thinking about since the von Braun era. They've been thinking about this since the 60s, and it is a more efficient way of getting us into space via rockets that are not chemically powered. Now, one of my guests, Mike Houts from Marshall Space Flight Center, sent me a NASA video that explains this quite nicely. It's only 3 minutes long, and it kind of helps sets the stage for what we're going to be talking about. I want to remind everybody, and I see you guys already on YouTube, so you guys are awesome. I see John and Andy and Superluminal and Peter, all you guys, so thank you for joining us. I'm streaming on YouTube, of course, and you guys know this, Twitch as well as Facebook and Twitter. And so all of those things can be coagulated into my coagulator, and I can read the comments and questions that you might have for our guests if you comment and leave them in the respective platforms. If you use the large question mark on YouTube, I can see those easier. It helps me to see the questions, and it's really good to be back again. So let me cue up this video. It's only 3 minutes long. Actually, it's 2 minutes, 49 seconds. And it explains a lot about what we're going to be discussing. So it's sort of a primer, if you would. So hold on, and here it goes.
First-generation nuclear thermal propulsion, or NTP, could enable both faster transit between the Earth and Mars and a series of advanced space missions. Nuclear thermal propulsion is powered by nuclear fission, which has been used on Earth for more than 70 years. How it works is conceptually simple. Energy from fission is used to heat hydrogen to about 4,400 degrees Fahrenheit. This hydrogen is then accelerated through a nozzle, resulting in a propellant efficiency roughly twice that of the best chemical rocket engines. Nuclear thermal propulsion was considered for use in the Apollo program, and significant development and ground testing was accomplished. Advances in technology since the 1960s may improve its affordability, viability, and acceptability. For example, it may be possible to fuel modern NTP systems with low-enriched uranium, instead of highly enriched uranium. In addition, it may now be possible to ground test NTP systems at established, safe, self-contained rocket engine test facilities. For human Mars missions, the physical size of an NTP engine is largely determined by the rate at which fission energy can be transferred to the hydrogen propellant. However, the equivalent volume of the uranium that would be split is actually quite small, roughly that of a toy marble. That energy is used to get astronauts to Mars faster. NTP can take months off the trip compared to using traditional chemical systems, reducing risks associated with exposure to galactic cosmic radiation, microgravity, and other hazards of deep space travel. The maturation of nuclear thermal propulsion will also facilitate the development of fission surface power systems, enabling a power-rich environment at any exploration location. Abundant power could also be used for in-situ resource utilization, life support, communication, and other diverse applications. First-generation NTP systems are a first step towards advanced nuclear propulsion systems capable of travel throughout the solar system.
Okay, I love that. I love that It sounded like one of those videos that you listen to when you're in high school and your teacher says, "Okay, we're going to watch a film strip right now," and he goes on to explain all this stuff in there. But I had never heard of gameon.nasa.gov. I think I'm going to have to ask my guests about this. Let me bring up everybody here. So here is my panel today. Joining me, let's see, in the upper left, I think is where you guys are looking, is Dr. John Horack. He is the Neil Armstrong Chair in Aerospace at Ohio State University. He's also the Senior Associate Dean of Engineering there. So welcome, John.
Thank you.
Also joining me is Dr. Michael Houts. He is from NASA's Marshall Space Flight Center, and he's the Nuclear Research Manager there. So welcome, Mike. It's good to have you here. And also Dr. Jonathan Witter. He is the Chief NTP Engineer for BWX Technologies, which is an amazing company. We're going to learn a little bit more about them here as we go on. So also welcome, Jonathan. It's good to have you here.
Thank you.
Okay, so we just got a little brief overview of what nuclear thermal propulsion is all about, and I loved how the video said it's going to improve acceptability of this technology. I guess it's a little bit scary, but there was also parts of it that were reassuring. Like we're really only using the amount of uranium that would be maybe marble size. The volume would take up about the size of a marble. And so let's start with you, Mike. I want to know about NASA's interest in this first. And then I'd like to talk a little bit with Jonathan about what they're doing to help develop some of this technology as well. So tell us what NASA is hoping to get out of this technology.
So with NTP, I mean, there's a lot of benefits when we do ambitious missions. And so one of the more ambitious missions that people talk about a lot are human Mars missions. And so with NTP on a human Mars mission, you can, for example, it opens up the opportunities to do faster round trips, possibly, cutting the round trip time to Mars below, say, 24 months, maybe down 22, 23 months, even for, what we consider first generation systems. And so that you're reducing the astronaut exposure, not just to radiation, but just having to be out there in a spacecraft that's going to be really hard to repair. If anything goes wrong, just the natural, the zero gravity, but also just the environment, and also just, again, being on a spacecraft that has to be very reliable for the entire time they're gone. So that's a big potential benefit. Of course, NTP also reduces one-way transit times to Mars. If, say, we wanted to stay away from Earth even longer, spend a lot more time on the surface of Mars, well, again, you can cut the transit times down. You can have a better launch cadence, and that would just be how fast we have to launch the heavy lift launch vehicles for supporting that kind of mission. You have really good abort capabilities with the NTP architecture. You can, for example, if you get a few months into the mission, you can still, basically turn around and come back to Earth. You don't have to go all the way to Mars and come back. And so that's one aspect of NTP. So it really just gives us a lot of flexibility, a lot of improvements over for those types of missions. And in cislunar space, people talk about lunar tugs, people talk about other applications of the cislunar space, and those are there. But really, it's with nuclear, it's the more aggressive, the more ambitious the mission is, the more it's going to pay off. And then really down the road, you have systems where you can, for example, you could use any volatile for propellant. As mentioned in the video, we don't need chemical energy to energize the propellant so that it, again, can provide thrust. We're using fission energy. And so there are system designs out there. We consider them second generation systems where you get a even higher specific impulse, but you can also use almost any propellant that might be available. And then also with the derivatives of NTP, when we got to the point where we need lots of power in space, say 100 kilowatt electric unit sizes or higher, then the NTP derived systems also look very good. And that's just really using the standard NTP core geometry, very similar fuels, very similar control systems, everything that we developed with NTP, but then hooking a power conversion subsystem onto that so that we could use that to generate electricity. So that's, again, further down the road until but again, typically that's say 100 kilowatt electric or higher power sizes. I will mention there's other really good options that we look at, say 20 kilowatts electric and less.
Okay.
So I just did what I didn't want to do. I just probably rambled for several minutes.
No. You did. No, that's what we wanted. That's what I asked you, and you answered it.
Well, you didn't use the word ramble, so I mean.
I want to remind you guys that I should have put this in the top of the intro. In the description box is a link to that video that I just showed you, where you can watch it. Don't watch it now because you're watching me, but you know that's there. And then I also put a link to something that this brings to my next question to Mike about with NASA. In my comment earlier about how this is something that I always thought would be done by now. This is not a new concept. NASA has been working on this since the 60s. There's a really great video also in the description box in YouTube where you can click on that and watch. It's about 23 minutes long, and it's I think it was made by Disney. I don't know. I'm not quite sure, but it's cool, and you definitely should check it out. I was pretty transfixed by it. So, Mike, this isn't new for NASA, is it? This isn't something that you guys are just thinking about. You've always been thinking about it, but we've been so focused on chemical rockets up to now, right?
Yeah. There's been, like you said, there was a tremendous amount of work done really from about 1955 to 1973 by NASA, the Atomic Energy Commission, just a lot of agencies working on it. And if anyone goes out online, you look under Rover NERVA program or NERVA reactor testing, there's dozens of really good videos out there. And so, again, a tremendous amount of work done during that time period. And we can use there's been a lot of advances in manufacturing, a lot of advances in materials, just overall vehicle design or computational capability. And so if we choose to develop these systems again, initiate a robust program, then we can build on what was done from 55 to 73. But there's also a lot of areas that we'll be able to improve on. I know Dr. Horack and Dr. Witter have a lot of very relevant research, relevant capability for moving things forward. And then also again, just linking it in with the whole idea of special, I guess you call them like special purpose fission systems in general. There's a lot of talk now about using, say, small reactors to power remote villages. And so you're not, obviously that's a terrestrial application, but remote areas, remote villages using very safe modern reactors. But it's amazing how much commonality space reactors we might consider using in space would have with those types of systems also, because again, you're trying to be extremely safe, extremely reliable, good lifetime, minimal maintenance, a lot of the same types of requirements.
Okay, so actually, hold on before I pull that up. So I'm sorry here, hold on, get my things right. So Jonathan, I want to talk to you next because I had not heard of BWX Technologies prior to this, and I went to the website and wow, this was pretty amazing, the stuff that you guys are doing. Your company seems to know about nuclear power of all sorts. You're involved in nuclear powered submarines. You're involved in nuclear fission in all parts. Now, from my naive perspective, nuclear power is one of those things that seems to have, from my perspective, and I know you'll dispute this, kind of got stuck in the 50s. We built nuclear power plants. Everybody was excited about them, too cheap to meter, all of this stuff. We kept hearing about how great nuclear power plants were. And then they built a few. And then I kind of thought the technology stopped there. But obviously, I'm wrong about that. Tell us a little bit about what you're doing and what, and specifically BWX Technologies is doing with respect to nuclear thermal propulsion. And maybe give us a guide about how wrong I am about advancements in nuclear fission along the way.
Right. Well, sure. Yeah. BWXT really has been involved with nuclear power since the beginnings, starting off as a steam boiler maker, and working on the early in the heyday of nuclear in the 60s, whether it was Atoms for Peace, converting the weapons program into commercial or public use. So whether it was space reactors, huge effort with NASA and the Department of Energy, which used to be called the Atomic Energy Agency, or Atomic Energy Commission, worked for power reactors. And the United States actually flew a SNAP reactor, one reactor, in space, a small couple kilowatt power system, and then did a lot of testing, like Mike mentioned, for NERVA rover, where they tested about 20 reactors in the desert, at developing the fuel, developing the reactor technology and the rocket technology at all sorts of different sizes. With BWXT is evolved over the years, working on commercial power plants and then also space reactors over the time. We worked a little bit on the NERVA program. Later genres of power systems for, say, SB100. In the late 80s, BWXT was involved with that. And then there was an Air Force project that got converted into a commercial project for space nuclear thermal propulsion for a particle bed reactor. BWXT was heavily involved with that effort. So over the years, as NASA and the government kind of comes and goes with what they want to do with nuclear thermal propulsion, at times BWXT has been involved as one of the industry partners, along with other university researchers and other industry partners to continue to develop the aspects. And most recently, we've been involved as part of the game-changing development office, which is that Game On NASA site, where they have, in fact, just this week, they're doing their entire program review, where they're kind of like the incubator program for NASA for looking at different technologies. So,
is that what that is? Is that what the Game On thing is? Is an incubator?
Pretty much.
Okay, I never heard of it.
A lot of really cool. If you go to their website and check out the different technologies that they're developing, there's some really cool little things that they're doing, ranging in kind of like the multi-year efforts to multi-million-dollar efforts. And NTP is one of the bigger efforts right now. We're coming to the end of a 3-year contract with NASA, partnering with them for reactor design development and then fuel element, because we're a manufacturing company as well as a design agency. We want to be able to build these reactors ultimately, and so that's why NASA partnered with us to try to develop the technology, bring it a step further than more kind of like the more recent paper studies. As Admiral Rickover would say for the Navy, well, you can have a dime a dozen paper reactors, but until you actually have to go off and build one, you find the true challenges of building and operating a reactor system, especially for a space system.
Yeah.
Where it's a high power dense system and you've got to make it low mass and provide the heat to heat the propellant.
Well, I'm going to go back to some of the details of the design here in just a minute, but I want to get John in on this just for a second. Dr. Horack, what are and I'd like for you, hopefully you can comment on another concern that I have, but I want to find out what you're working on at Ohio State with regard to this technology. And can you comment on some of the safety issues that are having to be, I mean, there's got to be some safety issues here that we got to worry about with respect to this technology. I was hoping maybe you could comment on that too.
So yeah, I can start with that.
Okay, good.
First of all, anytime you fly anything in space, even if it's a jug of water, safety is paramount. You're going to put something on a rocket. A rocket is a huge energy density machine. You're going to let all that energy go at once and accelerate that object just to get to low Earth orbit faster than the muzzle velocity of a gun. Space station is moving at almost 5 miles a second. So safety is already built into everything that we do in space flight. So that's the first thing. The second thing is that of all the nuclear systems you might want to fly on a spacecraft, this is the one that you want to fly because it has the potential to be the very safest. We have flown more challenging nuclear payloads into space. So for example, when we send spacecraft to Mars, the Mars rover, that uses plutonium. Plutonium is extremely toxic. It has very significant.
Are those the RTGs, by the way?
Those are the RTGs.
Okay, radiothermal generators.
Plutonium decay to make heat, and that thermal energy is converted into electricity. Plutonium's nasty stuff. Yeah. You don't want it anywhere near your body, and you don't want it anywhere near anyone who might be an adversary.
That's right. Cassini, the deep space probes tend to have these on them. Voyager had one.
All of them.
That's right.
So
That's right.
This is not something that we haven't done or don't know how to do. And in fact, the launch of a low enriched uranium nuclear thermal propulsion system, it's actually launched switched off, which is not the case with the plutonium reactors. When you launch a plutonium reactor into space, it's on and it's hot. So first of all, I think it's important to say we're very safe. We aim to be very safe anytime we fly something in space. And a low-enriched uranium nuclear thermal propulsion system is among the safest nuclear things you could decide you want to put on a rocket. Now, that's the safety issue.
Well, I'm gonna drill down on this in a minute about why is this why are you saying, because you're not qualifying it, but you're just saying it. So I'm hoping that things like radiation, the amount of radiation is not as much. Like you mentioned, plutonium is nasty stuff. Here we're just talking about enriched uranium. That's one reason why it's a little bit safer. But is it also because it's just not generating as much radiation directed at us? Is that
it's not generating as much radiation. It's actually not hot when you launch it. It's in a very quiescent, it's off. It's in an off state. The reactor's off. You don't turn it on until you get into space.
So launch, an explosion during launch or something like that isn't so scary.
Well,
it's never a good thing, but
day. When your rocket explodes, it's a bad day.
I'm not trying to say it isn't. It's just,
right.
but it would be a super bad day if it had plutonium on board, right?
Well, actually, we can go into that as well. There have been some launch accidents that involved radioisotope thermoelectric generators. We fish them out of the water and we put them back on a rocket and go. But this would not be a catastrophe. This would not be a calamity. It would not be, and thank goodness, so hopefully no humans on board, no one would lose it. There would be no loss of life. You'd have to go get your stuff out of the ocean, put it back together, and try again.
Okay, all right.
Yeah, and I guess to one clarification is a lot of times in the press they always call the RTGs nuclear power or reactors, and they're really just a heat source by radioactive decay of the plutonium element. Now, one reason why they like to use it, they look hard, high and low to find a different radioisotope to use, but the plutonium-238's got such a long half-life that they can go on these long duration missions. So for 20 years or more, they can have a power supply that works pretty well. The cost of that is that it's highly radioactive when you're launching it, and it's hot with the loads needed to create the amount of electricity that they want for the payload. Like Dr. Horack was saying, that for a nuclear reactor, you don't turn it on until it's up in space and the vehicle is already assembled. So it's not like we're launching these rockets off of the Earth, like you see SpaceX and ULA and NASA launching things. The rocket engine doesn't get turned on until it's in space, ready for the mission to start.
And just to elaborate on that, with the plutonium heat sources, of course, the plutonium dioxide itself is a very good compound, from a safety standpoint. As far as if you did get in an extremely severe accident scenario, and then you have iridium clads and graphite aeroshells. So those have been designed, highly designed to be very safe to launch. But again, as Jonathan and John also mentioned, though, with fission, you're essentially non-radioactive at launch. I don't know if you sent one of those pictures in, Jonathan, but you had the old rover Nerva test. You see people sitting right next to the highest power reactors ever built, and before they've been operated, again, I guess you'd say they're essentially non-radioactive. And then what's nice too is with the nuclear launch approval policy, with the low enriched uranium systems, it's really a risk consequence basis, and that just came out a couple of weeks ago. That's available online if anybody's interested. But it's something we now have a very quantitative set of criteria that make a lot of sense. They're based on EPA, what the EPA does, what the NRC has done in the past, and so it's that's helping move things forward also. But again, there are a lot of advantages with the low enriched uranium system.
Okay. So I do have some of these images, but let me. So unfortunately, I don't have time to queue it up properly, folks. But I'm going to show this one slide that was brought over. I think who brought this over? Was it you, John?
Yes, I think it's some slides that Mike and I have used in other presentations.
Okay, so I'm showing the one that says fundamental performance of nuclear thermal propulsion. If you guys want to have that up locally, go right ahead. But that's the one I'm currently showing, and it's showing the steps by which this thing is going. And so I want to talk about this in comparison with chemical rockets. Now, in a chemical rocket, most of us are familiar with how that works. We've got solid rocket boosters that fire and provide thrust. We've got these liquid, I think it's liquid hydrogen and helium and oxygen, correct? Or is it something else now that propels things chemically, the rockets chemically? We also have hydrazine for jets and things like that. But here we're talking about something that's what did it say? Twice as efficient? Is that right? As a chemical rocket?
Right, exactly. So if you think about it, all the benefits of using nuclear fission heat is that you just use the reactor as a heat exchanger, essentially. The uranium fissions creates heat from the fission products traveling really fast, and the energy given off from Einstein's E equals mc squared says, okay, I can have a lot of power and heat generated in a small area. The trick is to make sure the fuel doesn't melt, so you run the propellant hydrogen through it. We could run different gases through it, but the one that makes most sense is we can have a monopropellant tank and just use liquid hydrogen and convert that into supercritical high temperature hydrogen. And so the classic ISP, or specific impulse, or the efficiency of the thrust, we can achieve high ISP, or like 900 seconds in the rocket parlance, because we can get to high temperatures in the gas, but then using hydrogen, the low molecular weight. So the temperature divided by the molecular weight gives you a sense of what the ISP, or the efficiency of thrust, is. For a chemical rocket, the best one you can use is essentially burning hydrogen by oxidizing it with liquid oxygen. And you come out with essentially kind of a high hydrogen content steam out the back end. But the molecular weight of that gas is something like 11 to 18, much, much heavier than hydrogen. And because that mass number is in the denominator, that's a big impact on how high of an impulse you can get with a chemical rocket. So the highest you can really do with a hydrogen oxygen system is maybe about 450 seconds, meaning you have to have twice as much propellant in your tanks to be able to go the same distance. And so we can use one propellant tank, hydrogen, and we need less of it for the mission.
Okay, sometimes I like to put things in my words just to make sure I understand them and make sure I'm getting the thing right. I don't mean to, if I'm repeating you, it's not what I'm doing. I'm just trying to make sure I understand. So by taking this marble-sized or sugar cube-sized amount of fuel, uranium, enriched uranium in this case, you're fusing that to create heat, which then goes into a chamber full of the fuel, which is, in this case, hydrogen. And the hydrogen is what's providing the thrust, the impulse. And the trick here, and the reason this is more efficient, is that it's not burning with oxygen. This is being heated by nuclear power, which is a much higher energy source, much more much higher temperature, and it's doing it more efficiently, and you're getting a higher impulse out the rocket nozzle. Did I say that halfway correct?
Except for that the liquid rocket engines will actually have a higher exhaust chamber temperature because they're combusting. So we can't get that hot and gas temperature, but the benefit of having molecular weight of 2 versus say 18, we don't have to get as hot as a chemical rocket does.
Okay. So the key is how fast can you make the exhaust come out the back of the rocket? And there's two pieces of that. One is how hot can you make it? And two, how light is it? Because if it's heavier, it doesn't want to move as fast. And so the specific impulse that Dr. Witter had talked about is a measure directly of how fast the gas is coming out of the nozzle.
Okay.
So you can almost multiply by 10-ish. When you see 450 seconds, that's 4.5 kilometers a second-ish. When you see 800 seconds, that means the gas is coming out at about 8 kilometers a second. And the faster the gas can come out of the nozzle, the more efficient the rocket engine is.
Okay. And we're talking, and as you already mentioned earlier in the hangout, this doesn't get turned on until after we launch. So we're still talking about launching into space the normal way, right?
Yeah. You put it on an Atlas V, or you put it on a Falcon 9, or you put it on an SLS or something, get it into space, and then you use that engine, the NTP engine, to accelerate your payload away from Earth towards Mars or Jupiter or deep space.
Okay.
So this is what we call an in-space propulsion system, not a launch vehicle propulsion system.
Okay. All right. So I'm going to show now. This next slide is pretty cool. This is what we get out of using NTP. So I know you guys don't probably have this up locally, but to me the things that jump out is that we're looking at 160-day transit time to Mars. How much faster is that than what we would do with chemical rockets?
factor 3-ish.
So 3 times faster we can get
Yeah,
there.
it's we go to Mars on, there's a couple pieces to this, because we go to Mars on 22-ish month intervals, because with the systems we have to wait until the planets just line up right, and then we can launch. And so you're going to see here in the next couple months a bunch of missions to Mars, because we're getting into the right alignment. Now, there are sometimes we can't go because we don't have big enough rockets to do that. So the time factor depends a little bit on when you go, but to Dr. Houts' point, with NTP, you can open up the window. You can go a lot more frequently and at many different times, and you don't have to wait as long, let's say, for the planets to come into alignment. And even more importantly, once you would send, let's say, humans to Mars under a chemical rocket, you have to wait. And you have to wait until Mars and the Earth are back again in the same spot. So as Tom Petty said, the waiting is the hardest part. You know, this gets, I hate to say it, gets rid of Tom Petty, because we don't want to do that.
No.
This will allow you to more come and go as you please, so to speak, as opposed to having to wait for the celestial mechanics to line up, which then causes you to have to spend 850 some odd days, 900 days in space, because you've got to wait to go and then you've got to wait to come back.
Okay, so yeah, going through the bullet points here, all of this is great. It looks awesome. Mars missions are faster. The engines are lighter. We can carry heavier stuff. The mission turnaround time is faster. But I'm going down here to this last bullet point, and I'm seeing something called the Apophis asteroid mission. First of all, I need to know what LEU is. I don't know what an LEU is.
Okay.
LEU?
Yeah, what's an LEU?
That's low enriched uranium. So one of the challenges that game-changing development put upon us was to use a low enriched or proliferation resistant fuel. So so that's a challenge, because all the Nerva rocket engines were tested with high enriched kind of weapons grade enrichment levels. So one of the safety factors is to use low enriched or up to 20% enriched. So that's what LEU just stands for, low enriched uranium.
Okay.
The Apophis asteroid mission, that's left over from Jonathan Certain, who I'm standing in for today. So
Okay.
Dr. Horack may be a better person on what that mission might be.
Well, let me just set the stage real quick and say that Apophis is an asteroid that's due in its first flyby in about, is it 10 years now? 2029, right?
Close flyby.
Yeah, its first close flyby. It's going to do it twice.
Mm-hmm.
And it's going to get so close to the Earth, folks, that it's actually going to go underneath the satellite trail, the satellite envelope of geosynchronous satellites. It's going to get close. And so, Mike, is NASA going to use this stuff to maybe do some experiments with Apophis? Or it won't hit, by the way. Apophis won't hit us, at least not the first time. 2036, who knows? We'll see. Do you have any comments on what NASA has planned for?
NASA's obviously very interested in there's really just all the asteroids, all the near Earth objects, everything, and then there's a lot of different activities, especially as far as trying to identify them and kind of track them, verify what their orbits are. As far as any really specific technologies beyond that, that's still a lot of discussion, a lot of interest, obviously, but nothing. Beyond observing and the tracking and really starting to catalog all these objects, not too much definite yet.
Okay.
Asteroids can be hard to get to, because most of the objects in the solar system, let's say all the planets, the moon, the sun, the Earth, tend to, within a few degrees, lie in the same plane. We call that the ecliptic. But many asteroids have very highly inclined orbits around the sun, which are energetically very difficult for us to reach. And so with the advent of NTP, we not only can get to places that we can already get to faster, it gives us the energetics to get to interesting scientific destinations that we have a hard time reaching right now, just because our rockets are not powerful enough. Apophis is one example of an asteroid. It will come very close to the Earth, but there are many, comets and other solar system bodies that we would like to explore, but are hard to go to, or we just get there because when we have to send tiny spacecraft because we don't have very large launch vehicles.
Okay, so yeah, I get that you're right. It sounds like a big challenge with NEOs and protecting ourselves from these if they were to be on a collision course with us is getting to them is one of the biggest challenges. But with respect to NTP, is that a viable? Let's say we get there. Is that a viable technology that's powerful enough that could maybe alter the trajectory of an Apophis-sized asteroid or something similar? Is that a real thing that could happen with NTP?
Well, one point also is, with a high performance propulsion like NTP, you'd be able to get to an object sooner, faster.
Sure.
It would be further away from Earth, and at that point, altering the trajectory, the amount the trajectory would need to be altered wouldn't be as much. Basically, the further away from Earth that trajectory could be altered, the less it needs to be altered, and from that standpoint, you'd have some significant advantages from NTP as far as just as Dr. Horack mentioned, just the speed that we could get to objects as well.
And when you get there, you will also have the opportunity to use the power source of the NTP, perhaps, to generate some of the other power that you might need to move the asteroid around. So NTP can allow you also to arrive on station with a significant amount of power at your disposal.
That's actually quite a huge capability of this, isn't it? I mean, you mentioned it in the Mars video as well, where, these surface reactors, I mean, we could have a power just might not be an issue if we do this right. Is that right? I mean, we've heard this about nuclear power before. I know.
There's always an issue.
Right.
Okay, well, lack of running out of it. How should I put? Well, you know what I'm trying to do. I'm trying to be rosy about this and say we're not gonna. We have a lot of other worries, but power won't be one of them.
Yeah, I mean, we go to the outer solar system with with nuclear power because first of all, the sun dims as you go r away. It gets 1/r² less bright. So
right.
You want to go to Neptune? Well, you're not going to use solar panels. You're going to have some other way, and you need power to get there. You need power to stop when you get there, and then you'd like to have power when you're there. And NTP is a pathway that would allow you to have all three, because there's just no substitute for power when it comes to doing science or exploration or keeping people alive. You've got to have power.
Okay. Well, Gregorius has a really good question for you guys, so I'll ask it and then you guys can decide who answers. He wants to know, how do you transfer the heat between the nuclear material and the hydrogen gas? Do you pass the hydrogen directly through the reactor, or do you use an isolated heat exchanger?
Jonathan.
I'll take that one because that's exactly what we're up to, is looking at the concepts. Essentially, right now, you pass the rocket people call it the propellant, the nuclear engineers call it the coolant. So we pass that hydrogen past the fuel elements, and in this case, the fuel elements are looking like or a derivative of the Nerva engine, where it's just a solid block of metal or ceramic for the fuel that embeds the uranium inside this fuel body, and then there are coolant holes, much like just a simple heat exchanger, where you pass the hydrogen through the hole. So turbo pumps pump the hydrogen through the system. It gets pre-warmed a little bit in other parts of the reactor system to provide the driving force for the turbo machinery, and then it pushes that hydrogen through the fuel elements, which are just essentially a big heat exchanger block, and the propellant cools the fuel to keep it less than the melting point.
Awesome. Good question, Gregorius. Okay. Hans Milling wants to know, the hydrogen tank is a powerful bomb if it goes off. How much worse is, for example, helium than using hydrogen? The Hindenburg disaster with a Zeppeliner airship show how flammable hydrogen is. So can you use something, how much worse is, well, how big of a danger is this bomb? It's just
hydrogen is flammable in the presence of oxygen, but in space we don't have oxygen. And the challenge with the hydrogen that we're going to have is how to keep it cold, and how to keep it very cold for a very long period of time. So we're not talking about a Hindenburg situation in space. We're talking about a cryogenic fluid at extremely low temperature And that's our engineering challenge, how to keep all that hydrogen very, very, very cold for a very, very long period of time.
It sounds like a similar problem that James Webb Space Telescope has. They have to keep things super cold down there.
And in fact, that's where the liquid rocket engines, if you've got an oxygen tank and a hydrogen tank, there you've got the potential for those two fluids mixing and burning and exploding.
There's
so
your Zeppelin disaster.
Right, yeah. So NTP doesn't have it, the chemical rockets would.
Okay. Well, let me just get to Larry Keese's real quick, and then I'll move on to a couple that I have. Larry Keese wants to know, does less heat mean that the materials aren't as difficult to manufacture? You said earlier that the chemical rocket, nozzle rocket temperatures were higher. Does this mean that the materials involved in an NTP are easier to manufacture?
Well, I would say because we're reaching near the threshold of the melting points of the materials, or vaporization points of ceramics. So we're pushing the materials to the highest end. So we need to use very special high temperature materials in order to drive the temperatures up as high. It helps the nozzle by operating at lower temperatures, but you still have to have a regeneratively cooled nozzle section. Yeah. But it's really, we're really pushing the fuel elements to the edge of their temperature capability.
Darn you, space, when are you going to get easier?
These engines, whereas the space shuttle main engine, for example, operated for about 8.5 minutes, these engines may operate 3 times as long. And so you may be able to withstand 8 minutes of operation, but not 20. And so there's a little bit of apples and chickens here in terms of how we do the materials. Okay.
I'm going to read Joe Schultes' comment. Radioisotope power systems require, this is back when we were talking about the RTGs, radioisotope power systems require robust containment of the plutonium-238 oxide fuel from releasing to the biosphere in an accident. Reactor systems can be designed to prevent criticality for launch accidents. And I think one of you guys alluded to that earlier by saying that you just pick them up and out of the ocean and use them again. So... and Aloha Milton, I admit I use these launching from Kerbal without hesitation, even on highly experimental SSTO. Somewhat of a hypocrite. Yeah, so
Mike, do you use at NASA? Do you use Kerbal Space Program there at NASA?
Oh, I don't personally, but somebody might, yeah.
Yeah, it's a lot of fun. It's a lot of fun.
Yeah.
Okay, so Jonathan, where are you guys on giving us an engine that we can use? What's the status at BWX Technologies with regard to one of these NTP rockets?
Sure. Well, right now we're in the kind of like the end of the game-changing development phase of parts of it, and as part of that process, we were looking at looking at the feasibility of the concepts to use low-enriched uranium. And higher temperature capable materials. So we were focusing on refractory metal based core systems. And the challenges of using that are that you need to slow the neutrons down that come out of fission to make them nice neutrons to have a small reactor system. It
nice neutrons.
It gets into the complications of the reactor physics, but the easiest way to explain it is we need neutrons that are slow enough to get captured in the fuel and not in other materials, such that we can create a small enough system. So that's been the challenge of focusing on the low enriched systems with refractory metals, because the refractory metals tend to be somewhat poisonous. They also like the neutrons, so they compete with the uranium for the neutrons. So we've come through the feasibility assessment right now and getting ready to report out to NASA, GCD, and Mike Houts as the principal investigator on the feasibility of assembling this and really integrating it with the rest of the engine system. So this effort also included a lot of integration with the engine folks at Marshall and at Aerojet Rocketdyne to integrate the package instead of just focusing on the reactor itself. We wanted to really look at the integrated system and the nuances that the engine people need to be aware of that the reactor needs, but also we needed to understand what the engine folks would need or could supply to us. So we're coming through that now. It's still, GCD is really meant to kind of raise the technology readiness level up to a certain level. And we're kind of like at the early stages of that coming out of the, yeah, they did it back in the 60s with NERVA, developing it up to a certain point. And over time, they've had different looks at it. But this was another hardware exercise and a little bit deeper dive into the design. But it's still at the early stages because they said use low enriched uranium, use refractory metals in a moderated thermal system instead of a fast reactor. And so those were the challenges that were all brand new that we were charged to look at.
Okay, Mike, you have a comment on that? I mean, they sounds like they've got the proof of concept stage ready to go.
Yeah.
What is NASA ready to take this? Are we going to be doing a test firing soon, or what's next?
Yeah. So they've been having tremendous progress made on systems.
All right. Well,
let's talk for Mike.
Okay.
Mike.
You guys got to do that. Yeah. So, but anyway, Jonathan has been making tremendous progress. That's not what made me choke up. And so, actually, but so we've got a lot of good fuel options for the system, a lot of really good system designs. We have looking at systems now where you can get not just the 900-second specific impulse for your main thruster, but you can actually have an orbital maneuvering system possibly giving you about 500 seconds of specific impulse. And Aerojet Rocketdyne and others have done a really good job laying out the engine design for that. Again, options for just really integrating the NTP engine into a stage in a way that you have a lot of other stage benefits in addition to rather than looking at them separately. If you look at them in the stage, you get a lot of potential benefits. So I'll turn it over to John or Jonathan and get another drink, and I'll be right back.
Okay. Sorry we caught you on that. Yeah, John, you got any comments on what's next with this technology and where we're going? I want to see a firing, man.
Yeah, I mean, I can tell you what I would like to see happen. I would like, there's been both legislation with funding as well as executive direction. It's rare these days, perhaps, to see the legislative and the executive branch of the federal government aligned. But I think this needs to be something that NASA puts on the calendar and says, look, 2026 or so, we'll design around the fuel we've got, and it may only be 80% of the engine we want, but we're going to go make sure that we know how to do this, and we will light an NTP engine in space. Even if it's to drop a small science package on Phobos around Mars and then bring that back and deposit the spacecraft in the inner solar system. But the mission that I would love to fly is where you take the NTP engine and the spacecraft and you actually launch it into the sun, not at the sun, but
into the sun,
in towards the sun.
Oh.
And what happens is, as the spacecraft gets closer and closer to the sun, it starts speeding up because it's falling into the sun.
That's right.
And when you get to the maximum speed, that's when you light the engine. And it's called an O-berth maneuver. And it would allow you to zoom that spacecraft out of the solar system at a velocity that would roughly catch Voyager in about 9 years. So it's a little counterintuitive that if you want to get to the outer part of the solar system, the first thing you do is go into the sun. And then, as Chuck Berry said, you put your foot in your tank and you begin to roll.
Yeah.
That gets you out of the solar system faster than anything else. And it really brings the outer solar system in which we live, I'll say, closer in time, so that you're not waiting 9 years for New Horizons to get to Pluto with a Jupiter flyby, right. And all your starving graduate students are eating ramen noodles for 9 years. You can get there in a period of time that's reasonable with respect to a human's career and a lifetime.
Well, anybody who's watched Star Trek 4 knows that maneuver. So
absolutely.
Yeah. So that's right. So you go, you fly through the sun or around the sun, whip it around, and so. I mean, do we know roughly how long a New Horizons that would, let's say we try to do another one out to Pluto this way, how much, do we have an idea how faster it would get there?
Well, no, not any faster than we did before. We put the smallest spacecraft that was useful on the biggest rocket we had, waited till things were aligned, and used a Jupiter flyby, and that was about 9 years. That's the best we're going to do.
So this won't help. Doing the same thing with New Horizons on a NTP rocket.
Oh, NTP will help. NTP will cut it by a factor.
That's what I'm at. I'm sorry, I cut you off. I apologize.
Absolutely, no.
By a factor of what?
Maybe 3-ish, factor 3.
Okay.
Depending on how you do it and whether you use Jupiter flyby or not, and what the alignment is and those kinds of things. But that's that's kind of a walking around leaky bucket figure of merit.
Well, 9 years versus 3 years versus 9 years is certainly a much better. You don't have to eat as much ramen that way. So that's
That'll sell short your ramen stock. But yeah.
Well, that's something people don't think about much. I mean, the New Horizons team had to wait 9 years after they conceived of their mission to do any actual science. And, that's a career. I mean, that's a good chunk of a career anyway.
And a lot of stuff goes wrong in 9. Could go wrong in 9 years. If I got to build a spacecraft that lasts 9 years, or I got to build a spacecraft that lasts 3 years, that's a whole different cost ball game. It's a whole different reliability ball game, and things get simpler and less expensive the shorter the mission is, because you got to feed the Army while you're waiting.
Right. You got to keep that mission going. So Superluminal's got a good question. It started a little bit of a discussion on the chat. He asked, could you combine nuclear propulsion with an ion drive system? Instead of competing designs, they could be synergized. And that was followed up with a comment by Russell Joyner, who says that that's called a hybrid bimodal system.
Yep. Paper at the International Astronautical Congress last year by a student, Justin Clark, looked at exactly that. You'd have very high impulse thrust along with very high efficient continuous thrust to see how you might navigate the solar system with those two. Michael, you got anything to add on that?
Yeah, if again, some of the designs that are being looked at are very amenable to that. You could do a NTP, and then depending on what level of NEP, nuclear electric propulsion wanted, a lot of different design options. And again, looking at kind of the same, starting to get to the point where we're looking at using the same, say, fuel production capabilities, the same infrastructure that's going to be in place. But again, yeah, definitely a lot of potential to do one or the other, or optimize a system that would use both of them.
Okay. Now, Joseph Kohler's asking a question that let me read the question, then I'll ask for clarification. He's asking, with the new policy, and he doesn't say what new policy that is, how long do you expect it to take to approve it and get it through the Department of Energy and EPA? Does it have to be approved by those agencies before you can use this technology?
So the new launch approval policy, and again, it's available online. And
first tell us what it is then. Yeah, and then
okay, so it's just a new nuclear launch approval policy. It came out about a month ago or so.
Oh,
and
okay.
It's been signed, and it's basically for example, with a low enriched uranium system, the signature authority, if it was a NASA mission, would be the NASA administrator. Now that administrator, he's of course going to gather input from other federal agencies, and that's all spelled out in the document. But it's a very quantitative process, which is very important. In other words, it gives a basically almost like a risk consequence approach, but it builds on the all of the I guess you'd say the regulatory guidelines, things that have developed over the past 7 decades that we've been using fission systems on Earth. And so it's again, an excellent approach. And so that's it's hard to say a length of time, but I think it's safe to say that won't be people aren't concerned that will be a pacing item. In other words, if someone makes a commitment that they're going to launch do a fission system in space, they will start on that approval process, but they won't be afraid to have an aggressive schedule for fear of not being able to get through the approval process on time. So that's probably not making sense, but sometimes people get such fear of the approval process that would actually keep them from baselining nuclear on certain missions that had a very aggressive schedule. And this one, the types of analysis that need to be done, the agencies would be involved. It's straightforward, and it looks like a straightforward approach, and so it's a big confidence booster.
Okay, Oldie 184 wants me to ask you guys about something called dipolar force field propulsion. Do you know what that is?
That's Dr. Horack. Yeah,
right.
I don't know what it is, so I'm supposed to ask your views on it.
Looking more puzzled. So
yeah.
I don't know what it is.
It's a form of propulsion that uses a dipolar force field.
Okay. Very good. Okay, we are in fact talking about nuclear thermal propulsion, so I've never heard of it, so I don't know. Okay, so we're running out of time here, and I just want to get your views. So BWXT is a company that clearly has a lot of impressive experience with nuclear power. I mean, I put the link, by the way, to you guys' webpage on your website about NTP in the description box. But you guys do so many other things with nuclear powered subs and fission energy and all kinds of portable and varied ways. Is this going to happen? I mean, are we really going to get this for, say, maybe not Artemis as part of the next moonshot program, but are you guys confident this is the future of propulsion and throughout the solar system for us in whatever form, whether it's human beings or unmanned space probes?
Sure, I'm a real advocate for either nuclear thermal propulsion or as needed nuclear electric propulsion, or even the kilopower systems, because you need to build out that infrastructure for higher power levels that solar or battery systems just can't provide. So I think I would say we're hopeful that NASA would choose this. This is where it gets involved in the other mission directorates and propulsion systems kind of competing for reference architectures for different missions. And so we want to help NASA ensure that nuclear thermal propulsion is a viable option, and to bring it into the next level of technology maturation and make it a true technology demonstration mission to raise the TRL level such that it can become flight qualified and enter into the more rigorous, and yes, it'll cost more money to enter into that phase of development. But if you don't do it, and you don't develop some hardware and do some testing of the components and then an integrated test, you'll never have it available. So it's better to continue the project and keep it moving, or it's at risk of never being available in the future.
You guys have any other comments on it? I mean, I'd like to know when, what your thoughts are on using it.
I would like to see the agency, NASA,
Right.
dedicate itself to a goal that says we're going to design, launch, and try to light this in space. This is how it was developed in the nuclear navy. We didn't have the first time we put together a nuclear power system for a submarine, it was in a submarine. And I really don't want to test this on the ground. We got better ways to do it. We don't need to worry about doing it on the ground. The money is coming because Congress has been appropriating money for a mission. The National Space Council, the last time they met, they discussed this as a very important technology that NASA needs to develop for human spaceflight, for scientific research, exploration of the outer solar system, and other requirements that the United States has. Let's go fly.
How do you feel about that, Mike?
I mean, I think, building on both the comments, I'd heard people, on projects throughout industry, throughout universities, saying that they'd like to see fission do for NASA what fission has done for the Navy. And I think that's another way for it to be expressed. In other words, really just open up tremendous capabilities for NASA that we don't currently have. And so there is, I'll just say there's a lot of discussions you can imagine on what the best way that there is to make that a reality. But I'm personally very in favor of things that are very fast-paced and go on a fast schedule. And so that's now I think what's been talked about also is just try to do set a deadline for something that's very impressive, and then do what it takes to make that deadline. And of course, everybody uses the Apollo analogy, but I think that was fantastic. I mean, someone asked me the other day, well, how close are we to NTP now? And I'd say we're a lot closer to NTP now than we were to a Saturn V in 1961. I'll just leave it at that before I get
really. That's nice. That's very.
We could go real fast on this.
That's very encouraging.
Good to be an old NASA guy because you can kind of say what's on your brain. But anyway,
not always a smart thing to do, is it?
No, but I totally agree with Mike and Jonathan. I think you guys have put together a really good set of early TRL work, and we're ready to try this. And it won't be the perfect NTP engine the first time. It'll be a good one. It'll work. We'll say, oh, we know how to do this. Okay, now let's make it better.
Awesome.
Perfect's enemy of the good.
Yes, yes, exactly. Well, I'm going to have to stop it there because we're out of time. I want to thank my guest, Dr. Jonathan Witter. He's a chief NTP engineer at BWX Technologies. Dr. Michael Houts, he's the senior NTP guy at NASA's Marshall Space Flight Center. Dr. John Horack, he's the Neil Armstrong Chair in Aerospace and is also the senior associate dean of engineering at Ohio State University. So thank you all for joining us and getting me hyped about NTP. I didn't know much about it until I went to Von Braun and the Von Braun Symposium, and then I saw all kinds of really cool things about it. I'm very excited to learn more and keep on it. I'm hoping you guys might consider coming back in another future hangout and give us an update on where we are on this technology. So thank you all so much for taking time out.
Appreciate you having us.
Sure. Yeah. Thank you.
My pleasure. Okay. Well, I want to thank you guys so much for watching. This will be a VOD on YouTube, Twitter, Twitch, and Facebook. You can watch it. I'm still monitoring comments there. So we'll be able to follow up, or I'll follow up on various questions if you have any after watching the live hangout. So thank you all so much for watching. And as always, keep looking up.
So long.
So long, guys. Thanks.
Yeah, thanks to everybody.
All righty.